Welcome everyone who's here and everyone who's online. This is, I think, the last RSC seminar for this term. We're delighted to have Cranmer with us, who is an assistant professor in the applied mathematics department. His background mostly is astronomy, but he's also developed a number of software packages alongside that. And so particularly talking to us today about some of the work he's done for symbolic regression, libraries, and based in both Julia and Python. So yeah, welcome, Miles.
Cool, thanks. Okay, yeah, so happy to talk today. So I'm going to talk about SymbolicRegression.jl, which is a Julia library for doing solving this task called symbolic regression. So I'll kind of talk about what this is, why it's useful, how it works, and all of that. Okay, so PySR, I'll just say PySR is the Python front end to SymbolicRegression.jl. So PySR uses this nice library called pythoncall.jl, or the Python version, which is Julia call. It's basically like, you know how like NumPy and SciPy, they have C backend, so PySR has a Julia backend. So I really like this mode of developing because then all the Python people can use it. Okay, so PySR does symbolic regression. Symbolic regression is a machine learning task where the objective is to find analytic expressions that optimize some objective. So what an analytic expression is could be, you know, you could think of this as code. So code in some domain-specific language. So it's kind of popularized by John Koza, and then there's a paper by Hod Lipson in, I think, like 2008 that popularized it further. You can think of it, so if you think of it as like a machine learning tool, you can kind of visualize it on this chart as symbolic regression. It gives you high interpretability and it gives you high generalization performance for physics. I think the reason for this stronger generalization is that it has this very unique prior in the space of functions. So like neural networks are biased to learn smooth functions. Symbolic regression is, you know, it's biased to learn things that are sparse in terms of your operators. So if your operators are pretty good in general, if you enforce sparsity in that space, you tend to kind of find something that generalizes well. However, it's slow. It doesn't work great at high dimensional problems, although if your operators are high dimensional, you can kind of work around that. And it's not very expressive. Kind of, if your domain-specific library works well, you know, you can fit stuff, but if your operators don't cover everything, it's kind of limited. Okay, so the main tools are PySR, which is the Python front end to SymbolicRegression.jl. So this is a distributed high-performance framework for doing symbolic regression in Julia. Yeah, so SymbolicRegression.jl, it's a high-performance package for symbolic regression. I guess I'll also mention, because I thought this might be of interest to people. So PySR has resulted in a lot of different kind of other packages. You know, kind of half procrastination, half I get really annoyed at certain things and I write a package to solve it. So like one of them is type instabilities. I hate type instabilities in Julia. If you use Julia, you probably know what this is. So Dispatch Doctor is this library that was kind of designed to help prevent type instabilities from starting. So if you use Julia, it's kind of complementary to libraries like Cthulhu and Jet. But it solves it in a different way, and you can kind of embed it in your package. So this was designed to solve annoyances in PySR's development. I also get annoyed by race conditions a lot. That one's probably even worse. So I made this package called borrowchecker.jl. It's still fairly experimental, but it's basically like this layer of Rust-inspired syntax on Julia. So you can kind of force types to be immutable, even if the underlying type is mutable, and prevent write access in kind of like a borrow rules model. So it's still fairly experimental, but this is also kind of motivated by PySR, like having like really annoying bugs in PySR. The last one is performance regressions, which I also hate. And so, yeah, so I made this package called airspeed velocity, which is inspired by the Python version ASV, which is like, you know, if you make a pull request, it tells you the benchmark comparisons against the main branch. So it's kind of like continuous integration flavored version. Okay, so what is PySR? So they're flexible, user-friendly frameworks for solving symbolic regression. The default algorithm, it's not really like an algorithm necessarily. It's kind of a combination of many existing ones that has kind of merged together in this highly tuned optimized loop. There's not really any magic technique. It's just kind of a lot of stubborn engineering optimization with the goal of kind of making it really useful to the community. The origins were I was using this algorithm called Eureka, the software called Eureka, and then they started charging thousands of dollars for it. So I got really annoyed. And like every time I get annoyed, I kind of write, just write something to solve it. So PySR is like an open source alternative. And I think now it's actually more expressive than Eureka, which is nice. And so PySR is kind of born out of this need. I kind of consider myself a symbolic regression user, but I was kind of reluctantly a symbolic regression developer. And so, yeah, so that's why I'm kind of like, if you know the expression like dog fooding, I'm kind of constantly dog fooding PySR because I'm using it in my research. Okay, so symbolic regression, it typically works with a tree representation of expressions. There's kind of various alternatives, but normally you represent an expression by this, this syntax tree, and you evolve this as if it was like a genetic code for the expression. So if you have this data and you want to fit, expression to it, you would kind of manipulate this tree like it was, kind of DNA until it fits. So you can do mutations to it. You kind of swap operators, swap variables. That gives you a different, obviously, representation in the function space. You can also breed expressions. So if you have two different expressions, you can kind of swap subtrees of those expressions. These are basically just different ways of exploring this space of syntax trees. Yeah, and so you would do this until you get, find the match. So, okay, so I made this video that took me way too long to make, but it's done so you can enjoy it. It's kind of a visualization of how it works. So let me actually stop this. Yeah, it is minimum. Yeah. Yeah, so okay, so you start with this, this expression, and maybe it fits your data with some loss, whatever. You then perturb this expression. You either mutate it, you add nodes, delete nodes, crossover, whatever. And this brings you to a different space in this expression space. You then, you keep doing this process, you kind of explore all the different options until you get closer and closer to the ground truth. So this is a genetic algorithm, right? It's not doing gradient descent. It's kind of you're exploring this discrete space. Although SymbolicRegression.jl inside the optimization loop, there is like traditional BFGS optimization on the constants. So there's kind of like multiple algorithms stuck together. I'm going to play it again because I worked so long on this. You get to enjoy it twice. Yeah. Took me so long to get the transparency right. Yeah. Yeah.
maybe you'll come on to answer this, but how do you decide when to sort of genetically mutate versus when to start optimizing constant?
So the optimization is another type of mutation. So it's randomly done.
Okay.
And also it happens, so that's like that's one of the ways it could happen. It also gets called at the end of a loop. So you kind of have this one population of expressions that gets evolved. At the end of the, however many steps you do, it does a full optimization of everything. Then it sees like, okay, what's the population like? And then it starts over. So it's both like a mutation operator that changes the state of the tree. So it could be done randomly. Yeah, I'm happy to take questions through it. I like interactive talks. Okay, so there is both a Julia API and a Python API. Again, the Python API is managed with Julia call, which is this really nice, interface between Python and Julia. It's really nice because, I mean, Python has so many users that I think it's really a good idea to kind of expose your Julia libraries on Python, even if it's not as customizable. Like it just opens it up for more users. So a lot of this is the same as the Julia version. You kind of pass this list of operators and unary operators. You can also provide it with custom operators. So this is kind of one of the things that PySR can do that Eureka and other commercial versions can't, is you can very easily define custom operators, define custom losses. It's very customizable. So you can just write Julia syntax here, and it will evaluate it in the Julia runtime and put that in your operator list. You can also define a custom loss, right? So you can say, okay, given prediction target, I want you to do the squared error or whatever, and then fit. Yeah, so this is like a scikit-learn API. The Julia one follows MLJ, so there's an MLJ .jl API. Okay, so the way the loop actually works, you have this population of expressions. Maybe you have like 100 expressions in a list. At every cycle, you're going to randomly take some of those. So maybe you take two. You take two random expressions. Of those, you look at their losses and you see, okay, what's the best expression? You might also have a parsimony term, which looks at the complexity and kind of adds that to the loss. So you take the fittest of those, and then you have an if statement over mutations, kind of different weightings that these could randomly happen. You either mutate, do a crossover, algebraic simplification, or kind of traditional optimization. So you pick one of those, you get a new expression out, and then you put that back in your population. So this uses something called age-regularization, which kind of came out of the neural architecture search community, but it's basically like you just take the oldest member in the population, you kill it, and you replace it with the new one. It kind of gives like a natural regularization for the optimization. Yes, question online. Was there a question? Let me turn on my speaker. I think can you try again? Oh, maybe, I see, okay. Oh, maybe it was a misclick, okay. Or no, asked in the chat, maybe, no, okay. Okay, yeah, just speak up if you have any questions. Yeah, so this is the loop. That's basically the main part of this. You just go through this loop, like 100,000 times. It's not, genetic algorithms, they're not clever search algorithms, but these optimization spaces are just so nasty. It's almost like, I mean, it's not as bad as brute force. You're actually way better than brute force, but it's not at the level of like gradient descent where you can say nice things about convergence and all this stuff. But it's still much better than a brute force search. So PySR /SymbolicRegression.jl also has this multi-population aspect. So because in HPC, we often have many cores that we could use for optimization, the way SymbolicRegression.jl is parallelized is by population. So you have kind of many different populations of expressions, each of them with like 100 expressions each, and they evolve on cores, basically. So in Julia, this is like, either a distributed spawn or a thread spawn, and they're going to sit on different cores and evolve completely independently. And what you see when studying these populations is they tend to kind of specialize. So you'll get like one expression that has a bunch of like exponential terms, one that's like polynomial terms. And then after every cycle, there is a migration step. So they kind of, you randomly sample some of the expressions, you feed those back to the head worker, and it's going to like spit them out back to populations. So this is kind of how you mix this genetic diversity between the populations. There's also this thing called a Hall of Fame, which is like the best expression you've seen at every complexity. And that's kind of stored on the head node, and like, so you're always tracking the best expression ever seen. And that is also used to populate the populations randomly. Okay. Okay, so yeah, any questions on the algorithm side of things? I'm going to talk about the features and stuff now. Yeah.
Do you find when you're cross-populating at the end of this, all of the nodes tend to converge towards the same, at least maybe functional form, or do you find you get sort of different timings? I guess maybe it depends on what kind of thing you're trying to fit or maximize.
Yeah. It's honestly like very hyperparameter dependent. So if you have very small populations, they'll kind of like quickly specialize, but they'll also kind of quickly move all over the place because there's just not enough population to memorize like previous generations. But if you have maybe very large expressions, they'll kind of sit closer to where they started maybe. Yeah, I guess it's very hyperparameter dependent. Yeah. 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 Oh, I mean, well, the scaling up to is kind of, that's mostly just a function of like what I've tried. I mean, I think you could, like, you can't yet use GPUs effectively for this. I hope eventually we can, but CPU scaling, I've only done it to thousands. I mean, I think you could scale a bit larger. I think so it uses Julia's distributed.jl, which for kind of like all to head node, it's kind of slow. And it kind of scales, it gets slower and slower the larger the network. So I think I'd probably want to build an MPI functionality to get that working, but I'm very interested in that. Yeah, because potentially like it could definitely scale larger and larger. I think, like I think the algorithm itself is not necessarily limited. It's more the software side. Yeah. Okay. Any other questions online? Okay. Cool. Okay. Okay, API. So the API, like I said, it's actually fairly similar between the Julia and Python side. You pass in a list of operators. So you say, this is my search space. I want to find expressions with plus multiplication and then my custom operator maybe. These operators, it's quite flexible. You can actually have like discontinuous operators. They cannot even be defined over the whole real line. So you can say like, okay, if it's above 1,000, just return a nan, and that will work. And they don't need to be differentiable. So it's quite flexible here. So you can kind of define whatever domain-specific language that you want to use, and just kind of provide it here. You can also call external libraries. So, I mean, this is the nice part about Julia, like everything just kind of fits together. You don't have to worry about, oh, my NumPy array can't fit in the like PyTorch input, right? Like everything just kind of works and the compiler specializes it. So you can just put in a like an external package that defines a function, just give an operator using that. So the one requirement is you typically want to provide like you want to make your operators work on real numbers, maybe like that kind of. You can use it on integers, but you probably want to use it on real numbers. So, you might have to round to things like if you're using prime numbers, you might want to round to integers and then convert back to a float. But it is quite flexible. There's also a dimensional analysis feature. So this is, I mean, I think it's not as useful, but enough people were kind of asking for it that I finally capitulated and added it. This basically constrains the expressions to be dimensionally correct. So if you have like this feature is speed, this feature is distance, it will make sure that whatever expression it finds is dimensionally correct. You also have the option of allowing constants to have units or not. So you can say, I want you to be dimensionally consistent, but the constants themselves, you can choose the units. And that opens up your search space a bit. Or you can say, all the constants you find, they have to be dimensionless. So you kind of have both options. And it does kind of help the search space. For me, I haven't really found it useful, but I think some people like it a lot. Of course, you can also say custom loss functions. You can say like, okay, I want to do an L1 loss instead of L2. And this will, it just gets compiled into the function, right? Because it's Julia. So it'll just specialize to whatever operators or losses you provide. Now, one of the things that I'm really excited, which is a new feature this year, is called a template expression. So this lets you learn multiple expressions simultaneously according to a structure. So in this instance, I'm saying I want to learn two expressions, f and g, such that this is the actual output. So like if I want to fit like x, y, z to output, I know that my expressions always fit this form. So you can evolve f however you want, you can evolve g however you want, but the actual expression is going to look like this. So this is how it's evaluated. And this gives you like a huge amount of flexibility in terms of what you can do with PySR now, because you can evolve like hundreds of expressions simultaneously, and it all just kind of nicely sticks together because of like multiple dispatch. It kind of dispatches to subtrees automatically, which is nice. So this is like, it's my favorite feature at the moment. So, oh yeah, I made another video. This video is not as good, but it's just a screen recording, but it has some of the new features. Okay, so Symbolic Regression 1 came out earlier this year. It has these template expressions, parametric models, and TensorBoard integration. Let me scroll through. Okay, so this is kind of the Julia API. In the Julia side, you're actually writing out like the type parameters. So it's like, okay, two functions, one is f, one is g, and this is the closure for kind of how they're evaluated. And this is what's used in the SR regressor, which is like the PySR regressor in Julia. Okay, so let's say that we wanted to find this expression, and we know our expression is definitely of the form f of x times sine of g, y, z. Okay, so maybe this is the ground truth. This is what the output looks like when you're actually running the search. It says, okay, this is my expression I found for f. This is my expression I found for g. And you can also see, so now you can track it in TensorBoard, which is nice. So you can track like the individual expressions, the kind of Pareto volume, which is like this overall metric. Yeah, it's like if you don't, I kind of prefer using the REPL or the IPython version. It's just like a bit nicer, the output, but you could totally just track this in TensorBoard if you want. So it's in Julia, it's just based on the abstract logger interface. So you can pass any logger you want, And so you can also do like weights and biases or whatever. Okay, and I think the second part here, let me see. Oops. Okay. So another feature that was added is what's called a parametric expression. So some models that you want to find, they have different parameters in different regimes. Okay, so you have like, when my physical system is in this state, it's going to have this parameter and this parameter. But when it's in this state, it's going to have these other parameters. But the functional form is still the same. So you could think of this as like, I want to find a really good basis function, or I want to find a really good model that I can fit to different contexts. So parametric expressions let you do this. Let me see. Yeah, so you kind of say, so this is actually the old backend, but you can actually do this with template expressions now. You can just like co-evolve parameters, and it will fit, it'll evolve like the same functional form, but different parameter instances. Yeah, so I think like for more, if you're interested in that part where you're kind of evolving a basis function or like a model that can get tuned in different contexts, there's a few nice examples on the docs that you could check out. I think that's really useful. Like, if you just want to find a general model for some system, all you need to do is like say, okay, this is like class 1, and here's my data. This is class 2, here's my data. And it will co-evolve the expression and then the parameters of that expression. So you don't have like a single global constant. So it's I think it's pretty useful in different contexts. Yeah, any questions? Put anything. Does it make sense? Like yeah.
So you're saying you know which data is which regime?
Yeah.
And you ask it to know. So knowing that, find the different.
Exactly.
I'm just wondering, could you use this somewhere to actually take data and maybe discover different regimes based on how well it fits in one place?
I don't know. I mean, like, I think in that setting, what I would do is like cluster the data first, and then the clusters would be the class label. And then you can say, okay, I'm gonna have one coefficient in this space, one coefficient in this cluster, one coefficient in this cluster. But then you're finding a single symbolic form for all of them. I think that's how I would approach it. Yeah. Any other questions? Yeah, so I think like this is really useful in a lot of scientific contexts where you just want to model, but the constants could vary system to system or regime to regime or whatever. Yeah, so that's that. Another thing is that you can actually write any Julia code in the template, including multiple evaluations of the expression. So here what I'm doing is I'm saying I have expression f and expression g. I have variables x and y. And I'm going to evaluate the expression f 10 times recursively and then pass it to g. So it's like I'm integrating, it's kind of like I'm integrating a differential equation but I'm going to evolve expressions that pass through this functional form to generate my output. So this, I mean, it gives you like tons of flexibility, right? Because you can, this is just arbitrary Julia code. It doesn't need to be differentiable. It's just like a very flexible way to define a forward model given an expression object and data. So this also lets us learn vector expressions. So if you want to like evolve an expression for, I don't know, like, like a closure model in like, or you want to find a subgrid model for like fluids or something, you could evolve a vector expression with a specific symbolic form. So what I'm doing here is I'm saying I want 4 expressions. I want F1, F2, F3, and shared. Okay, 4 symbolic expressions. My overall symbolic form, it's going to use this shared expression, and it's going to add in like a per component term. It's like, okay, the shared expression plus F1, shared expression plus F2, those are like my actual predicted terms. And then maybe, so this is just kind of a hack to get the, because the output here needs to be a scalar. So this is just like a hack to kind of get the scalar output. But I mean, it really lets you like evolve tensor expressions, vector expressions, which might have shared components. And you might ask, okay, like, why does it need to use the shared component? It could just put everything in F1, F2, F3. So it's, remember, it's jointly optimizing loss and complexity. So it's actually going to try to put as much in the shared expression as possible and only put the stuff it needs to in like F1, F2, F3. So that's how this kind of works. Yeah. Any questions on this at all? Okay. Does this make sense? Okay. Okay, cool. Yeah. Another nice thing is this lets you deal with, multi-component loss functions. So say I don't want to work with mean squared error. Say I want to deal with negative log likelihoods. This lets me evolve expressions for mu and variance and use a proper negative log likelihood loss, right? So I'm evolving one expression for F mu, another expression for log variance, and then I'm putting them all together in a negative log likelihood. And so like it kind of gives you a whole framework similar to like deep learning, where I can just completely customize my loss for whatever objective I'm interested in. Only in this case, you're evolving symbolic expressions rather than this parameterized neural network model. But it kind of gives you the same level of flexibility. And I guess like, yeah, maybe another question you might have is like, okay, how does it know that like F mu is only one variable? So it kind of infers that by the first pass through the Julia code. It sees that, okay, this symbolic expression just is taking one argument. So I only need to evolve that expression with one feature. So that's kind of how it works. Yeah. So you could, you can evolve like expressions through a negative log likelihood. If it is differentiable, it will like differentiate it. So I think, so it uses optim.jl in the background, and optim will try to differentiate it. If it fails, it will just use finite difference. So if your combinator, like if your expression to combine terms is, if it's differentiable, it'll kind of use that in the constant optimization loop. Okay. I mentioned parameters at one point. This is actually how you define them. So in this setting, I'm co-evolving an expression with a parameter vector. Okay, so I'm evolving F. F is like a symbolic expression. And P is a parameter vector of length 2. So this is useful if I want to, I want to fix, like I want to find a constant here in front of my symbolic term plus another constant. And then I'm kind of unpacking it inside the expression. This is also how you would provide like class-specific parameters. You would just ask for more parameter vectors. I mean, like you could kind of ask for whatever parameters you want here, because it's just gonna feed them to like optim.jl and like co-optimize them with the expression objects. Yeah, so like if you have, you know that you want constants for like, I have 5 categories, therefore I want 5 different constants. So you could just pass it as like another feature to the function here. Yeah.
I was going to ask, why is a parameter not just another type of expression? But is that to do with what the pool that expressions pull from? As in, there could be lots and lots of different functions.
Oh, why are the parameters not expressions?
Yeah, why can't you not? Why can you not just lump them with expressions as being expressions that take?
Oh, yeah.
No.
Oh, you can.
Right. Okay.
So that will work too. If you define an expression object and you just do like f parentheses, that'll be equivalent to like a single constant. But the idea here is that, I want multiple parameters and I want to index it by category.
And so then my other question was, what is, when you tell it here, so f is going to be a function of those 3 variables plus parameters.
Yeah.
How does it know what functions to pull from?
So f is like this symbolic object, and when it's evolving, it will pull from the operators you specify.
Right.
So if you say like you can use plus, multiplication, division, cosine, f is just going to be exploring the space of those and like global constants.
Right.
So in this setting, when we say, we pass it 4 arguments, then the symbolic expression f is going to be evolving up to 4 feature nodes. So it kind of has 4 feature nodes to play with and like arrange them however it wants. Line.
I say, Richard, if you want to unmute and just ask, or I can ask for you. I will ask. So if you're passing in custom expressions as a string, I presume you don't get nice syntax highlighting and completion when you write that. However, is there anything you could do with non-standard evaluation so you don't have to pass it as a string and maybe get some of those niceties? Or maybe it's something that's easier to try and address with the development tool.
So the strings here are just because we're showing the Python API. In the Julia API, there's no strings. So I think if I go to here, you'll see that the template structure, it's just, you just write like Julia syntax. The strings are only because that is the Python API translation, right? We need to write it out as strings, and then the PySR utility functions are just going to do jl.seval to get the Julia version. So it's actually like it's evolving like, proper Julia objects. There's actually no strings in the evolutionary code. That's just like a Python API layer. Yeah.
Yep. Yes, thank you.
Okay. Okay, this is another crazy thing that actually worked, which I didn't think it would. But this is really new. This is like in the past month. You can now evaluate symbolic derivatives in the template. So if I have an expression f, a variable x, inside the template, I'm going to get an expression object f. what I can do is generate a symbolic derivative of f and then evaluate it. So this df object is just like another symbolic object, right? So d of f comma 1 is taking the symbolic derivative with respect to the first feature. It's creating a new object df, which is then immediately evaluated. So this code here is evaluating f of x plus f prime of x, and that is the return value. And so this kind of lets you add, like PDE loss terms if you want, or whatever kind of derivative expressions you want in the forward pass. You can just put those in the loss function. So this needed a new kind of autodiff library called dynamic diff, which is like built on these symbolic expressions. But it's pretty fast because it only has to compile the derivative operators. So basically just takes your library of operators, runs zygote on all of them, which gives you another set of operators. It merges them, and now it has like a big, library of operators. So maybe like if you have sine, cosine, it'll, double the number of operators, right? I mean, like, obviously that could be more efficient, but it's just like an algorithm. So it'll give you sine, cosine, derivative, sine, derivative, cosine. And all this df1 does is it kind of changes the operator index in your tree. So it's pretty fast. So what we can do with this is kind of evolve integrals. So let's say that we want to find this integral. Okay, so we have this symbolic integrand. We're saying, I have 1 divided by x squared times square root x squared minus 1. What is the integral of that? Does anybody know? Anybody want to guess? It's a bit ugly. Yeah. Yeah, so like say we don't want to work through this. We could just generate samples of the integrand. Okay, so I'm generating a bunch of data, so 1,000 points where I sample this integrand. I evaluate the integrand at those points. And then what I do is I write down my expression spec. So this is actually the old syntax. I just didn't update the video, but basically I'm saying I'm going to take the symbolic derivative of f with respect to its first argument, and I'm going to return that derivative evaluated at x. Okay, so I'm taking a symbolic expression and I'm just evaluating its derivative at the input x. Okay, so this is my specification of the expression objects. Any questions? Because this part is a bit confusing. So any questions? Any clarifying questions? Nobody asked a question. I'm assuming nobody gets it. I've got to do it again. Okay. Yeah, maybe that'll actually help. Okay, so I write down this expression spec, and then I want to evaluate it. So I want to fit, okay, so I'm going to say, this is my operator library. I can use plus, minus, multiplication, division, and I can use square root, okay? And I'm going to search for expressions up to this max length. So max size 20. Okay, that's my PySR regressor. I'm going to do a fit, and this is what it, oops, you can't see. Let me start it again, sorry. I gotta make my mouse go away. Okay, never mind. Okay, we do the fit, right? So it's evolving expressions such that the derivative of these expressions matches the integrand, right? It's like the dumbest way to take an integral, but it kind of works because you're just evolving it, and then you are taking a derivative in the loss function and comparing with the integrand. And it literally works, right? So this is square root of 1 minus 1 over x over x. which is the integral. Which is, yeah, it's the it's the dumbest way to take an integral, but it actually works like pretty well. So you could imagine doing this with like approximate integrals. You can do higher order autodiff too, if you want. I think like it'll kind of explode the operator space, so it might be expensive, but you could, I guess. Does this make sense, like what we're doing?
Yeah.
So we're kind of specifying the forward model and then evolving under that forward model.
Have you ever looked to see how robust this is? As in, how often does it get you to the analytical Mac versus something else that roughly fits? And I guess that's going to depend on the complexity of.
Yeah, I mean, it's very problem dependent. I mean, genetic algorithms are much less mature than I think other areas of machine learning. So there's not really like much theory about convergence and all this stuff. It's still like an empirical art. So, I mean, the rule of thumb is you just run it a second time and you see if it finds the same thing. And that's like, okay, maybe it converged or maybe it converted to the wrong thing. You know, it scales with complexity, it scales with the number of operators. So these are kind of things to worry about. The derivative operator is fairly new, so I haven't really explored that much, but you know, it gives you a lot of flexibility to explore. So you can kind of think of like, you know, I could do like a pin loss, right? So I could have like plus PDE terms so that my symbolic expression satisfies the PDE. I mean, you could solve like, you can kind of solve PDEs analytically by evolving the solutions, which is fun. Yeah, so I mean, you could, so this is kind of showing, let's combine everything at once. So we have our function object or our symbolic expression F. We're kind of evaluating it at different categories, taking the symbolic derivative of that, and then like, you know, recursively evaluating it. I mean, it's just Julia code, right? We're not, the point of this is to show that we're not really constraining the code you write, because this is just a Julia function on expression objects. So it's very flexible in terms of what you do. So it's kind of like a, you know, it's more of a framework now than a specific like routine. Oh yeah, one other thing I want to show is, so as a way to kind of show how hackable it is, I like to show this example where we evolve expressions on strings. So there is an interface inside SymbolicRegression.jl where you can say, like, I want to evolve an expression on this non-scalar type. And okay, you have to define the initialization function, the randomization function. There's like 4 functions you have to define. Once you define those, you can just evolve directly on your type. So we can do that for strings. So like, say I want to, you know, kind of evolve, I don't have like an intro to this, but it's basically like we're evolving expressions on top of strings. And you can see it's actually optimizing the literal string representation, like just with evolution. So I forget the exact expression. It was like you're concatenating strings and you're like reversing one, and then you have like this constant string, which is concatenated, and then you're kind of like zipping strings together. But it's cool because it actually evolves the correct expression. So this runs a bit longer. But you just define like the simple interface to say, this is how you initialize my type. This is how you randomly sample my type. And then it can just evolve expressions on it. So, you know, you could use this to evolve like tensor expressions, as long as you can say, this is how you initialize my tensor. This is how I randomly, you know, move between tensors. Then you can just evolve it. Because this, I mean, this is like, it's like a Julia sales pitch. It's like, it's so hackable. You can just, it'll just specialize to the type. Okay, I'm almost out of time, but I'll just like say a bit about the design internally. It's written in Julia. There is these 2 main abstract types. There's this abstract node type, which defines a single node of an expression object. And the type parameters are what value is like a scalar? So is this like a float 32, float 64? Is it a complex number? Is it a string? So that's T. And then we say, what's the max degree? It's usually just 2. It's just binary trees. Then this is the actual struct. So this is like a single node of my expression object. I say what the degree of that node is. So if it's 0, that's like a constant in the expression, or it's like a feature like x1, x2, x3. Then val is where I actually store the constant value. And then feature is an enumeration of features. So if I pass f like x, y, z, feature would go like 1, 2, or 3. Op is the index of the operator. So if I pass it 4 operators, op is going to be 1, 2, 3, or 4. And then children is just, it's recursive type. So it's like what are the children of this node? So it's like a f of, plus of x and y. This children would just point to x and y nodes. And yeah, so like the small design note is like, it was faster to use a tuple with kind of like poison nodes than to use a vector. Just like weird Julia optimization tricks. The actual operators are just a tuple. So we say that, okay, if I want to define like sine, exp, log as my unary operators, that's just the first thing I pass to this tuple. And the second thing is the degree 2 operators. So like plus, minus, multiplication, division. This will so because this is a tuple in Julia, this means the compiler can specialize. So whatever my library of operators is, Julia is just going to generate a new function specialization for that set of operators. So it's super fast. And it can like inline the operators. So it's like an enum of operators. So my expression objects are not, holding on to function pointers. They're just holding on to integers. It just says like, okay, I'm just like 1 if I'm this operator, I'm 2 if I'm a minus, I'm 3 if I'm a multiplication. So they don't have to hold on to these, these bulky function pointers. They just hold on to integers, which enumerate my operator enum. So that's the basic design. Then it lets you do this like, this ugly, lets you write these ugly kernels that result in fast sim kernels. So like whenever the user passes a new operator, Julia is going to define this new tight simmed kernel, just calling that operator. So this is like a fast version of this for those who speak Julia. It's like a generic version of this expression. Yeah. So this is kind of recursively called in the expression object. So it's just like checking integers. It's like, okay, is this integer 1? Then I call this operator. So I pass plus here, and then this operator gets called here. This is kind of like ugly, low level, like Julia expression generation, but yeah, it's just like evaluating a single operator. We also get to do operator fusing. So this goes up to 2 operators at once. So if you have cosine and plus in your operator library, it compiles a single kernel for like cosine of x plus y, and also like sine of x plus y, also exponent x plus y. So this is generated as a single simmed kernel, which makes the evaluation like, a little bit faster than if you just have single operators. But this only goes up to two operators. And this means you can, so if I evaluate like a Julia expression object, it's super, right? Because it's like compiling this expression and then evaluating it. So it's gonna be like 100 microseconds. But if I'm evaluating my, my enum type, it just goes through if statements and then calls the right kernel. So it's super fast. And I can like, randomly change the operator and I don't lose any speed. I don't have to recompile a new kernel. I'm just tracing through these if statements and calling the right simmed kernels. So it's fast. Yeah, I mean, like this is kind of other Julia stuff, but it's like easy to manipulate these trees because it's treated like a collection. Sorry, now I'm like spamming the okay, the expression objects themselves, I showed you the binary node, the binary tree. That's kind of like the low level. The user gets this object, which is an expression object. So it stores the binary tree, but also stores the operators in this metadata. And this is so that when the user gets it and it tries to evaluate this expression, like it actually knows what operators to call. But this isn't used as much internally because it can just like quickly manipulate the binary trees. Yeah, and then this is like, yeah, other internal types, blah, blah, blah. Uses a bunch of Julia libraries, uses cluster managers for the distributed compute. I think, I don't know, like I kind of want to use MPI. I'm still trying to figure that out. And yeah, so this is exposed to PySR for Python users and stuff. Oh my God, I have another section. Okay, I'm gonna skip. But it's like, I just want to show, oh yeah, this is like my favorite paper, I think. There's this machine-guided discovery of a real-world rogue wave model. I don't know what that is, but it seemed super cool when I read the paper. And so they kind of discover this, expression with PySR that fits rogue waves. So there's a bunch of cool papers like this of people using PySR for their domain science. So it's cool. This is another one with like black hole mass scaling. Yeah, and I've got like a list of other kind of applications. Oh my God, I had two more. Okay. Oh yeah. So this I kind of want to support the symbolic regression research community. So symbolic regression is actually kind of like splintered into different utility libraries. So there's dynamic expressions, which holds the expression objects. So you can use these fast sim kernels if you want to write your own symbolic regression code. Then there's another units library for fast unit evaluation. And then the derivative one is a separate library too. So this is good, like if you want to build symbolic regression library. And so it's very modular. So if you are writing a symbolic regression code, you can just like, include, you can just kind of subtype to symbolic regression. And then the user can just use the same like polished front end for your code. So it's kind of similar to PyTorch, but for symbolic expressions, where you can build like new architectures and it just all kind of works, which is nice. And you can like define, custom mutations, which is uses the multiple dispatch. Okay, cool. I think I'm at time. So, okay, summary, PySR symbolic regression are actively maintained open source symbolic regression libraries. They're kind of built to be, really useful machine learning tools for the science community. I think it's more broad now because you can define custom types, but it lets you learn expressions in your domain specific language that optimize some problem. Yeah, they're also kind of this framework for symbolic regression researchers. Okay, I'll stop there. Thanks.
Thank you, Rich. Are there any questions here or any questions online? You can stick it in the chat.
Yeah.
I have a question about open source project management.
Yeah.
How big is, what's your question? How big is the community contributors to PySR?
I guess, okay, so active, I mean, I guess it's kind of like a, like a Pareto frontier of activity. I think like the total number of contributors ever is probably like, I don't know, like 60, but the number of frequent contributors is mostly me and a couple PhD students. And maybe like, there's like a couple users who are like really actively using it. So maybe like 5 total really actively working on it.
The second question is, last couple of years, source maintainers have found much of what's you sort of drive by contributions from
Yeah.
That's actually experience.
I haven't yet. I mean, like some people will, you know, do little edits to the docs and README so that they can show up as a contributor. But like, I don't really mind those because they're fixing typos. Like, I don't know. I haven't really had, you know, junk, like total junk yet. Yeah. Yeah. Yeah, I have my speaker on, so if people want to ask online, just shout. I guess I'm a bit past time now. Yeah.
How do you balance sort of, or justify within the academic setting kind of development of software and tooling
Yeah.
versus sort of it's a tool to generate research, but
Yeah.
it's not generating those sort of box ticking outputs. Is that
Yeah.
something you've had to deal with?
I mean, okay, so it started as kind of a distraction, but it kind of turned into my research program, which is really nice. I guess like, you know, a lot of it, like I really enjoy, you know, coding. So I'm kind of like, if I'm trying to work on a paper, like sometimes I'll just make a new feature instead. And that's kind of been my main development mode. Yeah, but I mean, it does seem like because there's like a mix of, you know, papers from my group using it for research that it kind of justifies the time spent on development. And yeah,
I guess
I don't know. Yeah.
so. This is something I think the research software community sort of is fighting an uphill battle on. But how do you, when someone's using this in their research, how do you sort of get that credit back to the software?
So definitely like, you know, have easy bibtech so people can cite it, because now PySR has a lot of citations, which of course looks yeah. I think like, you know, I think it's good to, so one thing that I do is I have this page, or I think this link is actually broken, sorry, but if you go to the ai.damp.cam.ac.uk/PySR, there's a paper section with a easy way to kind of like submit a PR for someone's paper. And so researchers are incentivized to say that, you know, they submit their paper to my docs because their paper will show up at the top of my documentation, and it's like advertising for their paper for free. But at the same time, it helps me because, you know, it helps my research group because it's like, you know, we have this easy list of like, here's all the research that was done with it. And we didn't even have to like find it ourselves. It's like people just submit it because it's like, it's a popular software. So people, you know, they want to show their research off to the community of symbolic regression users. And it doubles as an easy way for me to kind of keep track of some applications.
So yeah, so we've been trying something very similar with we're developing.
Yeah.
Right. Are there any other questions online or in here before we finish up? Cool. In which case, if we could thank Miles once again, and we will be restarting the seminars again sometime in October, if you keep an eye on either the mailing list or the talks.cam page. Thank you very much.
Great. Thanks.